characteristics. So the transfer curve, we discussed the transfer and drain characteristics of JFET, and the transfer curve is not a linear curve. Drain current is not varying linearly with VGS, but instead it is following a parabolic equation. So the curve is approximated with parabola. Therefore, the equation which represents the transfer characteristics is VG ID equal to IDSS into 1 minus VGS by VP whole square. So this equation is called Shockley's equation. So Shockley, the scientist name, this is the equation which denotes the transfer curve. So there are questions coming in the semester end exam asking to derive the expression for GM. So this is nothing but the transconductance. Transconductance. So we will derive different expressions for GM. So first, what is GM? GM is transconductance. It means output current by input voltage. Output current by input voltage. Hello, ma'am. Ma'am, chep. Ma'am. First hour, ma'am. I think I'm free only. 1 second. I'll check my timetable. Tomorrow up to 10:30. Only first hour I'm free, ma'am. అవును. No problem, ma'am. ఓహో! సరే. ఓకే. No problem, ma'am. Okay, ma'am. So I think I need not inform them. Okay, ma'am. Okay, thank you. So the transconductance is output current by input voltage. The output current is drain current by input voltage is VGS. So whenever we talk about any transistor parameter, that will be the by default the dynamic. So we need to use change in the drain current to the change in the gate source voltage VGS. At a fixed VDS. At a fixed VDS. This is the definition of transconductance. At a fixed VDS, this is the definition of transconductance. Now we will derive this GM. Okay. So let us give this equation 1. So if I differentiate this equation 1 with respect to VGS, I will get transconductance. So differentiating equation 1 with respect to VGS, so dID by VGS is equal to IDSS, it is a constant, into So 2 into 1 minus VGS by VP. Since we are differentiating with respect to VGS, so again we need to differentiate this 1 minus VGS by VP, which is going to be minus 1 by VP. Minus 1 by VP. So dID by dVGS is nothing but the transconductance GM. So minus 2 by VP. I'm taking out all the constant terms at one place, into 1 minus VGS by VP. 1 minus VGS by VP. So first we have taken the Shockley's equation. This is the equation 1 represented here, which denotes, which is the mathematical representation of the transfer characteristics of the JFET. So transfer characteristic, it almost follows the parabolic. Therefore, the transfer characteristic curve is approximated to this equation, and it is given the name as Shockley's equation on the scientist name. So we are trying to find the different expressions for the transconductance GM. It has been asked many times in the semester and exam. So what is, from first, basically the definition of GM is transconductance, which is nothing but the output current by input voltage. So in JFET, output current is drain current and input voltage is VCS. So by default, any parameter is default the dynamic parameter. Therefore, we will write the definition in terms of deltas. So delta ID by delta VGS at a fixed VDS. So this is the definition of the transconductance. So to find the transconductance, which is delta ID by delta VGS, I can find this transconductance if I differentiate equation 1 with respect to VGS, then you will get easily the transconductance expression. Therefore, equation 1, I am differentiating with respect to VGS. So GM is equal to minus 2 by VP IDSS. So from equation 1, from this equation, 1 minus VGS by VP. So 1 minus VGS by VP, I can write it as, so ID equal to IDSS into 1 minus VGS by VP whole square. Now 1 minus VGS by VP, I can write this as root over ID by square root of ID by IDSS. So from equation 1, I can write VGS 1 minus VGS by VP. In place of 1 minus VGS by VP, I will write here ID by IDSS. So minus 2 by VP. So I can write this as root IDSS into root IDSS. So this under root IDSS will get cancelled. Therefore, I can write this as, so GM equal to minus 2 by VP root over ID into IDSS. So this is one form of, this is one expression in terms of ID and IDSS. In terms of ID and IDSS. So this is one equation which is asked many times, asking that prove GM equal to minus 2 by VP root over minus 2 by Vp into root over IDS in SS into ID. And another equation, next one, we will define transconductance. GM naught. GM is different, GM naught is different. So GM naught is the transconductance. It is the transconductance with VGS equal to 0. With VGS equal to 0. So GM naught, it is the transconductance with VGS equal to 0. So now the second expression, we will derive GM in terms of, sometimes derive the expression GM in terms of GM naught. So these are just for the sake of exam point of view we are discussing, otherwise nowhere we are going to use this GM naught, GM and all those things. So now the second one is, I will make use of this equation. I'll make use of this equation 2. I'm giving it as equation 2. So equation 2, from equation 2, I will once again write that equation 2, minus 2 by Vp into IDSS into 1 minus VGS by Vp. So if what is GM naught? GM naught is nothing but the transconductance GM with VGS equal to 0. With VGS equal to 0. So if I substitute VGS equal to 0 in equation 2, GM naught is obtained by substituting VGS equal to 0 in equation 2. So equation 2 is GM. So when it becomes when VGS is 0, then that transconductance is going to be called as GM naught. So therefore I can write GM. Now what we will get, GM naught is equal to minus 2 by Vp into IDSS. So this is GM naught. So equation 2 can be written as GM equal to GM naught. Now I am replacing this entire minus 2 by Vp into IDSS with GM naught. So GM naught into 1 minus VGS by Vp. So this is another form of transconductance in terms of GM naught. In terms of GM naught. So these are the two expressions which have been asked so many times. Prove that GM equal to GM naught into 1 minus VGS by Vp, or prove that gm equal to minus 2 by vp into root over id ss into id. So this is about the transconductance of FET. Now we will discuss a small topic, the small signal. So in the fifth unit, we have JFET formation, operation and current flow, VI characteristics of JFET, low frequency small signal model of FETs. Now we will discuss the low frequency small signal model. This we are going to discuss low frequency small signal model of FET. So low frequency small signal model of FET. So very easy it is. I think we have listed the differences between BJT and FET. Is it right? So these are there in the notes anyhow. The differences. Now all of you see here. I will explain without taking much time. I'll use these notes. So we have seen that from the working and current flow of FET, the drain current is a function of VGS and VDS. This we know very well. Drain current is controlled by VGS and VDS. Now, if VGS and VDS both are varied at a time, if VGS and VDS both are taking varying at a time, then the drain current is given approximately by the first two terms of the Taylor series expansion. So for this equation 1, applying Taylor series expansion to this equation 1, we can write the drain current as delta ID equal to, so we will differentiate this drain current with VGS, assuming VDS as constant. So the first term is differentiating the drain current with VDS as constant, and the second term is differentiating the drain current with VDS, assuming VGS as constant. So the Taylor series expansion is limited to first two terms. Now, if you observe ID by VGS, drain current by VGS, that is output current by input voltage, is nothing but GM, and so this is nothing but GM, and ID by VDS is nothing but inverse of drain resistance. So we have seen that VDS by ID is drain resistance RD, but here it is ID by VDS, therefore this is 1 by RD. So this Taylor series expansion, which is limited to the first two terms, now can be rearranged as delta ID equal to GM into delta VGS plus 1 by RD into delta VDS. So we are saying that we are trying to derive small signal model of FET. Small signal model of FET. So small signal model of FET means small signal model of FET means the variations in the drain current, variations in the drain voltage, variations in the VGS are very, very small. So delta ID is approximately ID, delta VGS is VGS, delta VDS is VDS. It means when we apply AC signal to an amplifier, the AC signal will be oscillating around its DC value. If you recollect the load line and operating point, all those things. So this is the center value is the DC, and AC signal is fluctuating or oscillating around its center value DC. So these variations in the fluctuations or oscillations around its operating point are represented with delta ID, which are very, very small. So delta ID is therefore represented with ID, and delta VGS is VGS, delta VDS is VDS. So therefore, in place of delta ID, I have written ID, GM into VGS, and VDS by RD. So this is the equation using which we will develop this small signal model of FET. Now see here, ID, if we take source here, gate, drain, gate, source and drain. So drain current is sum of GM VGS plus VDS by ID. So drain current is GM into V. There are two terms. ID is sum of GM VGS. So GM VGS. ఇక్కడ చూడండి, GM అంటే I by V into V. So GM means I by V, VGS is again a voltage. So GM into VGS, it is a current source, it is a current. So therefore now I represent GM VGS term with a current source. This is GM into VGS. And what about the second term? VDS by RD, VDS by RT. So drain current is two components, GM VGS and VDS by RT. So if I introduce a resistor RD, the voltage across this RD is VDS, then the current flowing through this resistance is VDS by RT, and the current flowing through this branch is GM into VGS. So if I apply KCL at this node, then the drain current, the current entering into this node ID is equal to the sum of the currents leaving. So current in this branch is GM into VGS, and the current in this branch is V by R, so VDS by RT. So if you apply KCL at this node, you will get this equation, so which satisfies this equation. Therefore this is the small signal model of FET, which has been derived from this equation, where ID is related with VGS and VDS. We know, so far we were discussing that ID is a function of VDS and VGS, but we don't know the exact relation. Now this is the expression which relates ID, VGS and VDS. So with this equation, the small signal model of FET is developed. And if you observe here in the model, there is no connection between gate and source. Only voltage is indicated, represented. That voltage is called VGS. This voltage is called VGS, and there is no connection between gate and source. And gate current, if I say gate current ID, it is approximately equal to 0. Why? Because if it is an N channel JFET, the gates will be P-type and we are going to give a negative potential to the gate. So VGS is going to be negative. So VGS is going to be negative. So therefore, in FET, the junctions which exist between the gate and channel are always reverse biased. So what will be the current flowing through the reverse bias junction? It is approximately 0. Practically, negligible current will be flowing. Ideally, the current is 0. Therefore, in FET, gate current IG is 0 because gate and channel junctions are always reverse biased. Junctions are reverse biased. So that is why there is no connection exists between gate and source. So just we will indicate the gate terminal and we will represent VGS. The amount of negative voltage applied between gate and source is denoted with VGS, but gate current is almost 0. So this is the small signal model of FET, and this will be used when we analyze FET amplifiers. So this is this model. So what do you mean by model of FET? Means this is the circuit. This circuit, it exactly behaves. The operation of this circuit is same as that of the physical operation of JFET, what we discussed in the previous classes. So therefore, this circuit is called as equivalent circuit of FET because this circuit is, it resembles the physical behavior of FET. This circuit, it resembles the physical behavior of FET. Therefore, this circuit is called as the model of FET, small signal model of FET. Small signal model of FET. And this will be used when we discuss about the amplifiers. So analysis of CS, CD, like common base, common emitter, common collector. Here also in FET, common source, common drain and common gate amplifiers. So wherever the transistor, wherever the FET symbol is there, wherever FET symbol is there, we will replace that FET symbol with its equivalent model. So this is also very, very important. Draw the small signal model of FET. Means you need to draw this circuit. You need to write this equation. If you can remember this equation, then it is very, very easy to draw this equivalent circuit or small signal model, because this model has been derived from based on this equation itself. So మీరు ఇక్కడ KCL apply చేస్తే you will get this equation, right? So remember this equation, then easily you can draw this circuit. So for 2 marks, it is important, draw the small signal model of FET. And in the last class, I forgot to indicate the regions. So in this notes, some extra topics are there. I will inform, I will remove those extra topics which used to be there previously. So mass capacitor or mass current equation which are not there for you right now. So excluding them, I will upload the notes. Okay. So we discussed that current increases linearly for small VDS, and after that, once the wedge-shaped depletion regions are getting formed, the rate of flow of the current decreases, rate of flow of the charge carriers decreases. So slope of the curve decreases, and at one particular voltage, drain current becomes constant. And if you further increase VDS, breakdown takes place. So here The this region, the region over which current is increasing linearly with voltage. So initially for smaller voltages of VDS, the channel acts like a constant resistor. So the portion over which current increases linearly with VDS is called ohmic region. It is called ohmic region. So this region can be called as ohmic region, where current increases linearly with VDS. Now, so the region where current becomes constant, it is called pinch off region, or it is also called saturation region. So this is similar to the active region where we operate BJT for amplification. So here in FET for amplification, to use FET as an amplifier, we will be operating in this pinch off region or saturation region where current is constant. And this region is called as breakdown region. So this is breakdown. These are the three regions of operation of FET. Breakdown region. So the initial region is a ohmic region. The initial region is ohmic region, saturation or pinch off region, breakdown region. So to use transistor FET as an amplifier, it will be operated in the pinch off or saturation region. So this is about the FET construction, the differences between BJT and FET, the drain and transfer characteristics of FET. We discussed the FET parameters. We derived the different expressions for the transconductance GM, and finally we derived the small signal, low frequency small signal model of FET. So it is called low frequency because this model is applicable up to audio frequencies only. So that is why it is called low frequency small signal model. So whatever model we discussed, that model is applicable only in up to audio frequencies. So that is why the name has given us low frequency small signal model. So in the next class, we will see MOSFET. What are the differences between MOSFET and JFET? So differences between JFET and BJT, differences between MOSFET and FET. So these differences are important for exam point of view for 2 to 3 marks. Yes, someone is trying to ask you. Who is that? So I asked sir to take attendance for 2 classes. I'm not going to upload attendance for this hour. So in the tomorrow's class, we will see